Welcome to WikiPodcast.
Right to be here.
Okay, so let's unpack this. You put together this great set of material, and we're going to dive deep into something that's, well, it's everywhere, isn't it? Shapes everything. But we mostly can't even see it.
That's exactly right. We're talking about the electromagnetic spectrum today. You can think of it like the whole family of light, really, stretching all the way from radio waves, the really long ones, down to tiny energetic gamma rays.
And it's all the same basic stuff, electromagnetic radiation.
Fundamentally, yes. But the energy level changes everything. It shows up in, well, incredibly different ways depending on that energy or its frequency or its wavelength.
Right. And our mission for this deep dive, looking through the stuff you sent over, is to get a handle on this spectrum. You know, why it's broken down the way it is, and pull out some key insights, history, properties, how it affects us.
Yeah, absolutely. And at its heart, the spectrum is just radiation sorted by frequency or wavelength. Higher energy means higher frequency and shorter wavelength. They're inversely related.
Okay, so high frequency equals short waves, low frequency equals long waves.
Exactly. And critically, higher frequency also means higher energy per photon, that little packet of light energy.
Got it. And that energy level determines how it interacts with, well, with everything.
Pretty much. It's one continuous scale, but the way it interacts with matter changes dramatically as you move along it. That's the key.
So we're going to journey across this huge range then, explore the different parts based on the material you've gathered.
Yeah, and what's really fascinating, and it's something the sources touch on, is that nobody knew this was all connected at first. It was discovered piece by piece over, centuries.
Right. For ages, it was just visible light, that incredibly narrow band that we can see.
Exactly. The ancient Greeks, they thought about light going in straight lines, bouncing off things. Newton famously used a prism, showed white light splits into colors.
The rainbow effect.
The rainbow effect. And then Thomas Young's experiments suggested light behaves like a wave, but it was all still focused on what our eyes could detect.
Until things started popping up in the invisible parts, like Herschel.
William Herschel, yeah, back in 1800. One source mentioned this great experiment. He split sunlight with a prism and put thermometers in the different colors to see which was warmest. And the hottest spot wasn't even in the colors. It was just beyond the red end. He'd found infrared radiation, heat radiation, essentially.
Wow. Sensing heat you couldn't see.
He called them calorific rays at first, didn't realize it was part of this bigger spectrum yet. And then, almost right away, Johann Ritter was looking beyond the other end, the violet end.
And he found
Something that caused chemical changes, chemical rays, he called them, what we now call ultraviolet. So you had these separate things, heat rays, chemical rays. Nobody knew they were related forms of light yet.
just weird invisible forces. So when did the big picture emerge? That it's all connected.
Well, Faraday made some early links between light and electromagnetism. But the real breakthrough, the prediction of the whole spectrum, came from James Clerk Maxwell, mid-1800s.
Ah, Maxwell's equations, famous stuff.
Seriously fundamental. His math described electricity and magnetism, and it predicted these waves, electromagnetic waves, that traveled at the speed of light.
So he figured light itself must be one of these waves.
Exactly. And crucially, his math didn't put any limits on the frequency. It implied these waves could exist at any frequency way beyond just the visible ones. That's where the idea of a full spectrum really came from, theoretically.
Even before anyone had detected most of it. That's amazing.
It is. And then Heinrich Hertz, in the 1880s, he was the one who actually generated and detected waves outside the visible range. Radio waves.
The first confirmation.
Yep. He showed they traveled at light speed, they reflected, refracted just like light, but with much longer wavelengths. Confirmed Maxwell's prediction. He even produced microwaves, though they weren't called that yet.
And the discoveries just kept rolling in after that, especially at the high energy end.
Right. Röntgen stumbling onto X-rays in 1895, suddenly seeing bones through skin. Game changer.
Must have been shocking.
Totally. And then Paul Villard found gamma rays around 1900 coming from radioactive stuff, even higher energy, even shorter wavelengths than X-rays. It took a bit longer to confirm they were also EM radiation, but folks like Bragg and Rutherford figured it out.
It's like putting together this massive cosmic puzzle. And the material also mentioned, sort of briefly, the whole wave particle thing, Planck and Einstein.
Yeah, the idea that light isn't just a wave, it also comes in these discrete packets of energy called photons. That duality is still central to how we understand light and the whole spectrum today. It's complex, but the spectrum itself is undeniable.
Okay, so let's get into the regions themselves. You said the names radio, microwave, infrared, visible, ultraviolet, X-ray, gamma ray aren't just arbitrary labels.
Not at all. It's a continuous spectrum, sure, but we divide it up because, and this is really the core insight from the material, the way the radiation interacts with matter changes fundamentally as the energy level goes up.
Ah, okay, so different energy levels trigger different physical processes.
Precisely. At the very low energy end, like radio waves, the waves tend to make charges oscillate collectively. Think electrons moving back and forth in an antenna.
Okay.
Move up in energy to infrared, and now you're talking energies that can make molecules vibrate or rotate.
Like jiggling molecules.
Kind of, yeah. Then you get to visible and UV light, and the energy is right for exciting electrons within atoms and molecules to higher energy levels, or even knocking them off completely, which is ionization.
Ionization that starts with UV, right?
Yeah.
And then X-rays and gamma rays are even more ionizing.
Exactly. UV is sort of the start of ionizing radiation. X-rays and gamma rays are much more energetic. They can knock electrons out easily, interact via different processes like Compton scattering. And gamma rays can even interact with the atomic nucleus itself or create new particles if the energy is high enough.
So the names reflect these qualitatively different interactions. That makes sense, even though the boundaries are a bit fuzzy.
Very fuzzy. And sometimes the name depends on the source, like X-rays versus gamma rays. Sometimes it's about whether it came from electron stuff or nuclear stuff. But the interaction type is the main idea.
Got it. Okay, let's start the trek. Low energy and radio waves.
Right. Longest wavelengths can be millimeters, can be many kilometers. Low frequency, low energy. Produced and picked up by antennas.
And the key thing is they travel well.
Yeah, one of the sources really emphasized this. We go right through the Earth's atmosphere. They can penetrate trees, buildings, mostly, which is why they're perfect for communication.
AM, FM radio, TV signals, cell phones, Wi-Fi, GPS, satellite links, radar.
Yep.
It's basically the backbone of modern communication.
Absolutely. Those long waves just keep going, bending around stuff. Essential.
Okay, moving up slightly. Microwaves.
Shorter than most radio waves, centimeters down to millimeters. Still pretty long, though. Generated by specific devices, klystrons, magnetrons.
Like in a microwave oven. That's the magnetron, right?
That's the one. And yeah, that oven use highlights their key interaction. Certain microwave frequencies are really good at making water molecules wiggle rotate, and that friction heats things up. Bulk heating.
So it's not just for leftovers.
Haha, no. Crucial for radar, like weather radar or air traffic control. Lots of satellite communications use microwaves. And of course, many Wi-Fi systems operate in the microwave band too. They penetrate materials pretty well.
The sources also mention this terahertz gap between microwaves and infrared.
Ah, yeah, the T-rays. That region's been technically tricky for a long time. Hard to make good sources and detectors.
Right.
But that's changing. There's a lot of research into using them for imaging, security scanning, things like that. Though water vapor in the air absorbs them strongly, which is a challenge.
Interesting. Okay, next up, infrared. IR, Herschel's discovery.
Right, the heat radiation. Wavelengths from about a millimeter down to around 750 nanometers, just below red light. It's often split into far, mid, and near IR.
Why split it up? More interaction
Yeah.
differences.
Exactly. Far IR interacts with things like how molecules rotate or lattice vibrations in solids. But again, water vapor blocks a lot of it, making the atmosphere opaque, though there are some windows astronomers can use.
Okay. And mid-IR.
That's the stuff radiated by objects at room temperature or body temperature, like the heat you feel coming off a person or a warm engine. It gets absorbed by specific molecular vibrations. This is super useful because different molecules vibrate at different frequencies.
Ah, the fingerprint thing one source mentioned for identifying chemicals.
Precisely. It's a cornerstone of analytical chemistry. You shine mid-IR light through a sample, see what frequencies get absorbed, and bam, you know what molecules are in there.
That's cool. And near IR.
That's closest to visible light, wavelengths just longer than red. It interacts more like visible light, involving electron energy levels. We can't see it, but sensors can. It's used in fiber optics for data, TV remote controls, some night vision.
Okay, finally, the bit we know best. Visible light.
The main event for our eyes. But, as the sources emphasize, it's such a tiny, tiny fraction of the whole spectrum, roughly 380 to 760 nanometers.
And it's no accident our eyes evolved to see this part.
Seems unlikely. The sun puts out most of its power right in this visible range, so evolution favored creatures that could use the most abundant light.
And all the colors we see, the way the world looks, That's just objects absorbing some visible wavelengths and reflecting others.
Pretty much. Our eyes detect those reflected wavelengths, sends signals to the brain, and the brain constructs our perception of color and shape. It's amazing. And of course, photosynthesis, the basis of most life on Earth, runs on visible light energy.
But still, just a sliver. Okay, cranking up the energy now. Ultraviolet.UV.
Just beyond violet light, wavelengths from about 400 down to 10 nanometers. Now we're getting into enough energy per photon to start causing chemical changes directly, even ionization.
Ionization meaning knocking electrons off atoms.
Exactly. It can break chemical bonds. That's why it's damaging to living tissue.
A sunburn, that's the classic example.
Yeah, specifically UVB, which is in the middle of the UV range. The material highlighted how it causes specific kinds of DNA damage. Thymine dimers, which can lead to skin cancer. That's why sunscreen is vital. It blocks UV.
Does all UV reach us?
Thankfully, no. Our atmosphere is a great shield. Nitrogen and oxygen absorb the highest energy UV, the vacuum UV, and the ozone layer is crucial for absorbing most of the dangerous UVB. What gets through most easily is UVA, the lowest energy UV. It's less damaging per photon than UVB, but there's more of it, and it still contributes to skin aging and some cancer risk.
UV also has uses, though, right? Like fluorescence.
Oh, yeah. It makes certain materials glow, used in forensics, checking counterfeit money, sterilizing things with germicidal lamps.
Okay. Higher energy still.
Yep.
X-rays. Roentgen's discovery.
Definitely ionizing. These photons pack a punch. They tend to interact via something called the Compton effect, where they scatter off electrons, losing some energy. Or they can knock out inner shell electrons in atoms.
And the key property is penetration.
For hard X-rays, the higher energy ones, yes.
Right.
They go through soft tissue, but are stopped more by denser materials like bone. That's the basis of medical X-ray imaging, radiography. Also used in airport security, industrial inspection.
Seeing inside things. And in space.
Whoa, absolutely critical for astronomy. Really hot, violent things emit X-rays matter swirling into black holes, superheated gas between galaxies, stellar corona. But like the highest energy UV, the atmosphere blocks them completely. You need telescopes in orbit, like Chandra.
Right. Space telescopes. Okay.
Yeah.
Top of the energy chart. Gamma rays.
The most energetic photons known. There's no defined upper limit to their energy or lower limit to their wavelength. Traditionally, the distinction from X-rays was often about the source.
Source meaning.
Like, X-rays often come from energetic electrons changing states, while gamma rays typically come from processes within the atomic nucleus, radioactive decay, nuclear reactions, or from really extreme astrophysical events or particle interactions.
And they're really penetrating.
Extremely. They interact via Compton scattering, like X-rays, but at very high energies. They can even do pair production. The photon's energy converts directly into matter, an electron, and its antiparticle, a positron.
Wow. So uses, besides blowing things up in sci-fi.
Well, again, hugely important for high-energy astrophysics. Observing things like supernovae remnants, active galactic nuclei, gamma ray bursts, the most powerful explosions in the universe. Again, need space telescopes.
Anything more down to Earth?
Some specialized uses. Sterilizing medical equipment, sometimes food irradiation to kill microbes. Occasionally used in radiation therapy for cancer, though other radiation types are often preferred. And they're involved in PT scans for medical imaging, though indirectly the scanner detects gamma rays produced when positrons emitted by a tracer annihilate with electrons in the body.
Okay. So pulling it all together, this whole spectrum, from radio to gamma. It's one thing, EM radiation, but the energy level changes everything.
That's the big takeaway from all the material, I think. It's continuous, but the way it interacts with matter shifts dramatically. Collective electron wiggles, molecular jiggles, electron jumps, ionization, nuclear interactions. It's all dictated by that energy per photon.
And that's why we give them different names and why they have such wildly different uses. Heating food, talking on the phone, seeing the world, getting a sunburn, checking for broken bones. It all comes back to where that radiation sits on this energy scale.
Understanding the spectrum really is fundamental. Physics, technology, astronomy, our whole view of the universe relies on it, and realizing just how much of it is completely hidden from our direct senses.
Yeah, it's quite the journey we've taken conceptually,
Yeah.
from those kilometers-long radio waves Hertz first detected, all the way up to these incredibly energetic gamma rays from cosmic explosions.
Yeah.
And the source is really made clear it's the interaction that defines the regions.
It really shows that what our senses perceive is just, well, it's a tiny slice of reality.
Absolutely. Which brings up a final thought, maybe for you listening. Thinking about how little of this vast spectrum our eyes can actually see, it raises a powerful question. What other fundamental parts of reality are we simply not equipped to perceive directly?
That's a deep one to ponder.
Thanks for listening. Write us your opinion in the comments on that very question. What other fundamental parts of reality might be beyond our perception? Subscribe to the channel to help more listeners reach our episodes. Thank you and have an amazing day.